At the end of this video lecture, students will be able to diagram and describe the bonding process involved for covalent molecules, and students will be able to calculate the enthalpies of reactions using bond enthalpies. Covalent bonding is characterized by the sharing of electron pairs between atoms, and it usually occurs between two or more nonmetals. However, metalloids and nonmetals can also form covalent bonds. So as you can see from our pictures here, hydrogen and carbon are sharing pairs of electrons to satisfy the octet needs of each. So hydrogen ends up with 2, and this carbon ends up with a total of 2, 4, 6, 8 electrons. So the sharing of these bonds, or sharing of these electrons, creates these types of bonds. Now this is in contrast with, say, ionic bonding or metallic bonding, in which electrons are either just a diffuse kind of puddle or pond, or sea, as metallic bonding is typically described as, or in ionic bonding where electrons are actually transferred between atoms and subsequently bonds formed by electrostatic interactions. So how does a covalent bond form? Well, first of all, you have individual atoms that are floating around, and what happens is as they get into close proximity to one another, the nucleus of one of the atoms, okay, is going to attract the outermost valence electrons of the other atom. Okay, and the same is going to be true for the reverse process, where the nucleus is going to be attracted to the outermost electrons on the other atom. Okay, and as they begin to attract one another, they get closer and closer in proximity. And eventually, once those once those atoms get into close enough proximity, what's going to happen is your bond is going to form. So this occurs when the electrons in those nuclei basically reach an optimum distance. And this allows for overlap of the orbitals in a way that minimizes any repulsive forces that would be brought on by nuclei interactions, and basically gives you the covalent bond. So bond polarity is going to have a big impact on the overall reactivity and characteristics of specific compounds. And bond polarity is going to be dictated by the electronegativities of atoms involved in covalently bonded molecules. And so the behavior of each of these types of compounds, or the various compounds, are going to be dictated quite a bit by the differences in bond polarity. So we'll look at the details here in a minute. But first, let's go ahead and take a look at electronegativity and what that means. So as a refresher, electronegativity is the attraction an atom has for an electron in a compound. Okay, so we know that fluorine is our most electronegative element on the periodic table, and we know that the closer we get to fluorine, the more electronegative we become. Now, whenever we're looking at bond polarity, we have to look at which element is the most electronegative in that set. So if we look at this compound here, we see HCl. So we have hydrogen and chlorine involved in this covalent bonding set. Okay, and if we look at this table, we see that hydrogen has an electronegativity value of 2.1, and chlorine has an electronegativity value of 3.0. So chlorine is the more electronegative of the two elements. So when we look at the distribution of electrons inside that compound, the compound, or the atom in that compound that has the higher electronegativity, is going to have a partially negative charge on its surface area. So in the opposite of that is obviously the one with the lower electronegativity value is going to have a partially positive charge on its surface area. So these types of charges, or these dipole moments as they're called, are going to dictate some of the behaviors of the compound. So let's go ahead and let's look at this a little bit more in depth. So we can look at bond polarity, or bonds, with respect to the percentage of ionic character that they possess. So the percent of ionic character that they possess is going to be dictated by the differences in electronegativity. So the larger the differences in electronegativity, the more ionic the character of the bond. Okay, so what does this mean? This means that if you have large differences in electronegativity, electron transfers will occur. If you have no differences in electronegativity, you have completely even and clear sharing. And if you have somewhere in between, you're going to end up with a bond that kind of has a hybrid orientation. And we're going to look at that. So nonpolar covalent bonds are covalent bonds in which the electrons are shared 100% equally between the atoms in the bond. Okay, so if we take a look at this, okay, right here, if this is a nucleus and this is a nucleus, right, the electron density that's being shared between these two atoms is shared evenly across the two atom centers. Okay, and we usually see this with atoms that are identical. So, you know, H2, Cl2, N2, all those diatomics that form molecules are going to be sharing in a nonpolar covalent weight. So we don't have any dipoles, there's no partial positive or partial negative charge. What we have is a completely nonpolar bond. So in contrast to the nonpolar covalent bond, a polar covalent bond is a covalent bond in which the electrons are not shared equally. And this results in the dipoles that we were discussing earlier. Okay, so this usually occurs between elements that have, fairly significant differences in electronegativity values. However, the differences are not so significant that we end up with an ionic bond. Okay, so in this situation, if we look at the atoms here, this is the central nucleus of this atom, this is the central nucleus of that atom, okay, and in a polar covalent molecule, you're going to end up with the electron density being shared unevenly amongst the two atoms. So the atom that is more electronegative is going to, by definition, have more electron density surrounding, while the one that has less electron density is going to be obviously less surrounded by electrons, or less likely to be surrounded by electrons. And this leads to those dipole moments that we were suggesting or talking about earlier. So this symbol, delta, okay, delta minus, delta positive, so basically it's just representing a partial positive and a partial negative charge. So what that means is that there's an area of negativity around this atom, and there's an area of positive charge around this one. It's not a full and complete charge, but there is a positive and negative aspect to the sides of this molecule. So if we go ahead and take a look at the electronegativity values that correspond to each element on the periodic table, we can look at and decide what type of bonding we have in a more quantitative type of way. Okay, so if we look and consider a few bonding setups, so let's look at fluorine, okay, diatomic fluorine, HF and NAF, okay, we can calculate the differences in electronegativity values for each of these and subsequently come up with and decide whether we have an ionic, polar covalent, or nonpolar covalent bonding type. So if we go ahead and look at this, the electronegativity value for fluorine is 4. Okay, so 4 minus 4, because they're both fluorines, is going to give me 0. If I come down here to this chart, I can see that a electronegativity value difference of 0 is going to give me a nonpolar covalent bond. Okay, so fluorine and fluorine bonded to each other gives me a nonpolar covalent type of bond. Now, I would have known that because I understand that when you bond two of the same atom types, you end up with a nonpolar covalent bond, but it's nice to see a quantitative approach to it. HF, if I take 4 for my fluorine and I subtract out hydrogen's 2.1, okay, that's going to give me a value of 1.9, okay. In the case of HF, if we come down here to the chart, notice that we're in the range of the polar covalent bonding type. So HF is going to be a polar covalent bond. Okay, and if we do the same type of calculation, okay, with sodium fluoride, so fluorine has electronegativity value of 4. Okay, sodium has 0.9. This gives me an electronegativity value of 3.1, which is way above what we need for ionic characteristics. So we know in this case we're going to have an ionic bond. Okay, so this is a more quantitative approach to this. The thing I want you guys to make sure that you're paying attention to, though, is that as you get into this polar covalent region, okay, when you're talking about the bonding of two nonmetals, if you have anything that's around 1.9 or on the higher end and it's occurring between two nonmetals, you're going to call it polar covalent. So even if it's slightly above 1.9 and it's occurring between two nonmetals, you're going to still call it polar covalent. Now, in that same thought process, when you're dealing with metals and nonmetals, okay, you're going to typically call them ionic, even if they, fall in the polar covalent range. So I don't want you to take these numbers and just blindly apply them. You still need to consider the type of element that you have in this bonding procedure or bonding process. So make sure you're paying attention to those details. So if we look at the distribution of electron density, in the case of nonpolar covalent, okay, bonding, that electron density is being shared evenly across those two atoms. Okay, in the case of polar covalent bonds, where we have an electronegativity difference that's bigger than 0, right, we're going to have these partially positive and partially negative portions of the bonding structure. And in ionic compounds, remember, we completely transfer electron density, so I have a completely negative and a completely positive ion. Understanding the difference between these and understanding what kind of compounds are going to form polar covalent or nonpolar covalent bonds, it's going to be very important for you to understand intermolecular forces, melting points, things of that sort. So we want to make sure that our skills here are very strong. Now let's go ahead and let's discuss the strength of covalent bonds. Okay, and before we do that, though, we need to understand something called bond enthalpy. And basically what bond enthalpy is it's the change in enthalpy associated or related to the breaking of a bond in 1 mole of a substance. Okay, so if I have 1 mole of chlorine and I want to find out the bond enthalpy, I'm going to measure the amount of energy I have to put into that mole of chlorine to get it to break into its corresponding chlorine atoms. Okay, so when we look at this, we're going to always notice that bond enthalpy is always going to be positive. And the reason why bond enthalpy is always going to be positive is because we always have to put energy in order to get the bonds to break. Okay, remember, bonds are forming so that everything can be stable, so we can lower the overall energy of atoms. Okay, we want everything to be quote-unquote happy or quote-unquote lower in energy. So bonding occurs so that that lower energy state can be reached. Now, when we want to disturb that lower energy state, we have to put energy in order to return to the higher energy state. So with respect to bond enthalpy, okay, the higher your bond enthalpy, the basically stronger your bond. So the more energy you have to put in, okay, the more energy you have to add to a substance in order to get bonds to break, that means that you have stronger bonds. You have better overlap. And we'll talk about those details here in a little while. But something else I want to point out is that bond enthalpy will be represented in this way. This is referring to a chlorine-chlorine single bond. Okay, so the value that you would get off a chart would correspond to this chlorine-chlorine single bond, and basically you could look up the enthalpy value associated with a chlorine-chlorine single bond. So you could figure out how much energy would have to get put in order to break that chlorine-chlorine single bond. Now, bond enthalpies can actually be used to calculate enthalpies of reaction. So we can figure out delta H information by utilizing bond enthalpy values from the back of the book or from tabulated data. Okay, and so if we want to calculate our delta H of our reaction, our enthalpy of our reaction, we can take the sum of the bond enthalpies of bonds that are broken, so whatever gets broken up, which in this case is going to be reactants, And we can subtract out the sum of all the bond enthalpies of all the bonds that are formed. So that's going to occur with the products. So if we want to look at the calculation specifically for this type or this reaction here, what we have is the combustion of ethane to give us CO2 and H2O products. So the first thing we're going to look at is we are going to essentially look at how many bonds are being broken and what kind of bonds are being broken and what kind of bonds are being formed in this process. So if you look at this delta H calculation here, okay, on this side or this portion of the equation, you're going to have the number and type of bond value or bond enthalpy value, and that's going to be considered for every atom, or excuse me, every bond that exists inside the molecules. Okay, so if we go ahead and we take a look at this, we have 2 molecules of ethane. Okay, and so ethane in this case has 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, but there's 2 molecules of it, so we have a total of 12 carbon-hydrogen bonds that we have to account for. Okay, and then if we look at the carbon-carbon bonds that exist, we notice you have 1 in each molecule. I have 2 molecules, so in this case I'm going to use the bond enthalpy for a carbon-carbon single bond, and that's going to be multiplied by 2 because I have 2 molecules of ethane that are going to experience this bond breakage. Now in this situation I have O2, oxygen. Now the back of the book or your table may represent this, right, in this fashion. Okay, notice this is an oxygen-oxygen double bond. The way it's been presented here is that O2 is just presented as a specific number, but you do want to make sure that you're looking at the type of bonds present. So in this case, the back of the book gives it to us just as O2. Okay, it just assumes that that's double bond is intrinsically understood. Okay, and I have 7 of those. Okay, so it's going to be 7 times that O2 bond enthalpy value. Okay, so I'm going to plug in the values that I get from the table or from the back of the book. Okay, and that's going to give me the bond enthalpies of all the bonds that are going to be broken on that reactant side. Now, this same exact process is going to be carried out on the right-hand side, but in this situation, now I'm looking at the bonds that are being formed. Okay, so in this situation, I have 2 carbon-oxygen double bonds. Okay, in each molecule, and I have 4 molecules that are produced. Okay, so 4 times 2 is going to give me 8 carbon-oxygen double bonds. Okay, in the case of my H2O over here, each H2O molecule has a set of 2 hydrogen-oxygen bonds. Okay, so if each molecule has 2 hydrogen and oxygen bonds, okay, and I have 6 of those molecules, that's going to give me 12 oxygen and hydrogen bonds. So once again, I get those numbers off the bond enthalpy charts. Okay, I plug in the numbers, I do the multiplication and the addition and subtraction. This subsequently gives me the number of kilojoules released during this reaction. So the combustion of ethane is going to release negative 2,831 kilojoules of heat. So we expect combustion reactions to be exothermic, so this seems reasonable in terms of your calculation. So you can use these bond enthalpy values in order to calculate delta H of reactions. So I want to make sure that I'm stressing that not all bonds are comparable. Okay, so when you're looking at these types of calculations and you're looking at the formulas and the structures, you must be able to write correct Lewis structures in order to figure out the correct bond enthalpy values to plug into these equations. Okay, so if you have no idea what kind of bonds are occurring, you're not going to be able to do this type of calculation. Why? Because if you look at, a carbon-carbon double bond versus a carbon-carbon single bond versus a carbon-carbon triple bond, all of these have unique bond enthalpy values, right? Okay? And because of that, understanding how to write proper Lewis structures is going to allow you to see what the molecule looks like, what kind of bonding you have, and subsequently allow you to use these bond enthalpies. So, strong Lewis structure writing is highly important for these types of calculations. So, talking about that same bond enthalpy value setup, okay, if we look at our carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond, notice that your bond enthalpies are increasing as you add additional bonding. Okay, so as I said earlier, knowing what kind of structures you have is very important for you to be able to get the correct bond enthalpy value in your calculation and subsequently allowing you to figure out your enthalpy change for a specific reaction type. Now, not only does the bond enthalpy increase as the number of bonds increase, but also this is going to correspond, or these number of bonds are also going to correspond to the distance between the atoms involved in the bonding process. Okay, so the stronger the bond enthalpy, okay, the more bonding you're going to have. Okay, we understand that. Now, the more bonding you have, the shorter the bond. Okay, so a shorter bond length is going to happen when you have more bonds. More bonds you have, the higher your enthalpy. So what does that mean? That means that basically in order to break a triple bond between two carbon atoms is going to take more energy than breaking the double bond in a carbon-carbon interaction, and even more energy than the carbon-carbon single bond. Okay, so bond lengths and enthalpies and all of these relationships that we see here, we want to be able to understand them and feel comfortable with them. Make sure you've made the connection between the lengths of the bonds and the number of bonds present, as well as the amount of energy you would have to put in to break them apart.